Hello. Today on Consider the Following, I'd like you to, well, consider the following. You and I are sitting on the Earth's crust, and it seems pretty solid, doesn't it? But now scientists believe that the Earth's crust is actually made of plates. Not cheap plastic picnic plates like this, but tectonic plates. And tectonic is from the Latin word for build. So the Earth's crust is built of plates. Plate tectonics. And the plates are floating on the Earth's mantle, which you know is molten metal. It's kind of like corn syrup. In fact, scientists actually use corn syrup like this to do studies of what's underneath the Earth's crust. Scientists first caught on to the idea of tectonic plates when they realized how well South America seems to fit in next to Africa. Not that bad. So take a look here. Here we have the camp stove of science. And in it we have models of tectonic plates. See, right now they're all together. And scientists believe that at one time, all the plates of the Earth's crust were one piece called Pangea. And Pangea, well, that means whole Earth, see? Not that bad. Let's say this is the Earth's crust. You see, where the plates, the tectonic plates, are spreading apart, that's where we get volcanoes. And where the plates are coming together, that's where we get mountains. Now, you know, the plates are still moving even today. In fact, North America is moving away from Europe about this much every year, about 2 centimeters, about an inch every year. Well, thanks for joining us on Consider the Following.
Okay, it's real important to have shades on in here, glasses, because sometimes things will pop in here. This is molten glass. Watch what happens.
The Science Guy. Take a look at this. It's a mountain. Well, actually, it's a volcano. Volcanoes are formed when hot, molten rock from deep inside the Earth finds its way to the surface. Now, this isn't hot, molten rock. It's a mild acid. And to help it find its way to the surface, we'll add some sodium bicarbonate. This will be like hard rock. Right. Above the molten rock from deep inside the Earth. See, the pressure builds up and it builds up. Then eventually a volcano will erupt. It'll blow its top. It'll explode.
When?
Anytime now.
Okay.
There it goes. You're saying, Bill, you know, I've made volcanoes like that in my kitchen. Maybe better. I mean, that's it? That's it? I mean, what's the big deal? What's the big deal? Take a look. Volcanoes can blow down entire forests in just a few seconds. They can reroute rivers and form new lakes, carve new valleys, transform entire landscapes in a matter of hours. And that's what happened around here, when that mountain right there blew its top. It's Mount St. Helens, and it erupted in 1980. It's in the Pacific Northwest of North America. Now, there are different types of volcanoes. They don't always explode when they erupt. Some volcanoes ooze. Now, when I say ooze, I'm talking about hundreds of thousands of tons of rock. At well over 1,000 degrees Celsius. They come out of the Earth and they cool off to make new land. Land that you and I live on. See, there are different types of volcanoes, but they all do the same thing. They all build up the Earth's surface.
Since the Earth was young, volcanoes have hurled fiery rock from the planet's interior to its surface.
The Richter scale is a way to compare the size of one earthquake to the size of another. ground can move in all different directions, but to start out with, let's say it's moving up and down, like this. See how we have a nice smooth curve? That's from the ground moving this way. Now let's say we have a bigger earthquake with a bigger ground motion. Let's say we have one 10 times as high. Like this. See how this one is 10 times higher than this one over here? So then the ground would take on a shape something like this. Same nice curved shape, but this stack of chips is 10 times as high as the one over there. But look how many more chips there are. You see, it takes a lot more chips to keep the curve in the same shape. The chips are like the energy in an earthquake. So when the ground moves 10 times as much, it has a lot more energy, about 32 times as much energy. And we have 32 times as many chips. Now, because the numbers can be very small or very large, Richter came up with the idea of using tens. See, let's say we have an earthquake of magnitude 1. Well, it's going to have some ground motion. We'll call it 1. Now let's say we have another earthquake of magnitude 2. Well, its ground motion is going to be 10 times as much. We just add a 0. Then for an earthquake of magnitude 3, we add another 0. So look, an earthquake of magnitude 3 has 100 times the ground motion of an earthquake of magnitude 1. And it has a lot more energy. Now, since Richter came up with this, a lot of other scales have come along. But they all work in about the same way. The bigger the magnitude, the bigger the earthquake. And the bigger the energy there is to knock stuff over. You weren't supposed to see that.
Oh, sorry.